Go for it.
Sweet. So my name's Ian Macfarlane. My supervisor is Daewon Jung, sitting right there. And we've been working in John Bowers' lab, I've been doing LIV characterization of epitaxially grown indium arsenide quantum dot lasers grown on silicon substrates. Kind of a mouthful, but first let me kind of bring in what something like this is used for. So how many of you have looked at a computer kind of specifications label in the past few years and seen the label like dual core, quad core for the processor? Yeah, several of you. So that basically means on a CPU chip, so this is kind of a rough diagram, they put multiple brains on the chip, and so it's on a chip you have actual individual kind of processing cores, and if you think about it, it's kind of fairly intuitive, but if you work with multiple people, like 4 brains or 2 brains is better than 1, so you'd think the same works for computers, and it is true. The issue, though, is because when you introduce multiple cores to a computer, there's a slowdown in between those cores, and part of this is just working together. If you think about it, if you were working in a group project, when you're working by yourself, you can just kind of think through a problem, but when you're working in a group, then you have to kind of slow down, format your thoughts, actually explain it to other people, so make sure you're on the same page. Same thing for these computers. The issue also is that with electrical components between the cores, this slows down connection speed, and then you have this kind of slowest point of operation, which kind of maximizes how fast your core can operate. We're looking to replace these components with optical components because then we can increase the speed of the core as a whole. We've known for a long time that optical components can be better than kind of electricity and copper-based things, and this is the fiber length, for example, doesn't matter as much for these applications, but we would like to be able to apply photonics kind of principles and the advantages of it on a small scale inside a computer, as well as kind of already the application on the big scale. So my group is specifically focusing on growing these quantum dot lasers on silicon, mostly because silicon substrates are cheap. If you look here, this is a diagram given to me by Daewon. Other 3.5 substrates can cost like 25 times the cost of a silicon substrate just per area, and silicon wafers actually come in much larger sizes, so there's kind of advantages to building on that. The problem with growing on silicon, though, is that when you're trying to epitaxially grow on it, you have a lattice mismatch, and so with the silicon substrate layer, as soon as you try and grow some kind of 3.5 material on top of it, you have dislocations that show up, and these dislocations can kind of thread up through the material, and then they can compromise your active region in the laser, and then when you have your electrons kind of moving around to do stimulated emission, which is what you want in the laser, if they instead fall into these dislocations, then suddenly they're doing this as opposed to working as a laser, which you can imagine is non-optimal. So then part of the approach to these, to kind of nullifying these dislocations has been to use quantum dot technology. So modern commercial lasers are all based off of a technology called quantum wells. And so inside a diode laser, you have a basically planar region called an active region, and that's where you have your stimulated recombination, which then it causes the gain region for lasers, and you have coherent emission. The issue with that is because in a quantum well, so if you imagine this is a plane here, so this is where the electrons recombine and what you pump light through in order to get a coherent beam, they're free to move inside this plane, and so if you have dislocations going through it, their freedom of movement works against you because they can easily kind of run into the dislocations and escape as leakage current, or be expressed as heat, which is also not good. So instead we're using quantum dots, which is, as opposed to just kind of planar confinement, it's a complete confinement. So when the electrons enter the quantum dot, they're kind of stuck there. And so while the dislocations are still kind of affecting the material, if you use a lot of quantum dots, you might only have say you have a density of 100 quantum dots per dislocation, you might have one quantum dot affected, but you still have 99 more that work just fine. And so this is an image of actually carrier-mounted versions of the lasers I've been characterizing this summer. And you'll see here, these are Fabry-Perot ridge lasers. And in the middle here is the actual laser cavity, and then there's a P contact and an N contact. What I've been doing is LIV characterization of these lasers. So I probe the lasers, run kind of steps of currents through them, measure their optical power and the voltage as well, to extrapolate things like the threshold current and the wall plug efficiency of the laser. And I'll go into both of those in a sec, but just for some perspective, these lasers here, the width of this chip as a whole is probably about like 1/8 of the width of your finger. So they're pretty small. So then here's LIV. So LIV stands for light current voltage, and it's a battery of tests that kind of show you multiple features of the laser, which I talked about before. This is kind of the power as a function of current curve that you can see as part of it. And the two features we really care about in something like this is the threshold current down here. So if you'll notice, at really low current injections, there's actually no lasing, but then it kind of jumps up. And so the point where it starts operating as a laser is really important, because if you think about putting this in computers, they don't have access to super large currents, so you want your laser to actually work at the proper current injections. Also, we're looking at max power, because if you think about it, if we can increase the power emitted by the laser for the same currents, then it's just a more efficient laser. I've also been doing temperature characterization for these lasers, so they work at room temperature, but testing kind of how the threshold and max power degrades over increased temperatures. The highest we've gotten so far for the Fabry-Perot lasers has been 8, but we're looking to drive it a little farther. So the two big results from my research this summer have been specifically characterizing really low thresholds in the lasers, as well as high wall plug efficiency. So the thresholds are really important, because if you think about in a computer application, you only have access to limited power, but beyond that, the thresholds actually deteriorate as you go. So a threshold of 3 milliamps after continued usage could eventually turn into a threshold of 5 or 6 or 10 or 20. And so if you're putting this in a computer, that basically determines the lifetime of the component. And so there's a real kind of reason for wanting to have as low thresholds as possible. On top of that, wall plug efficiency, which is a term I've been throwing around for a while, simply means the efficiency of conversion between electrical power that you put into it and the optical power you then measure. And we've actually seen a highest wall plug efficiency of 38%, but we're looking to kind of drive that higher as well. Last thing that's also pretty important is we're looking to kind of, this LIV testing has been in preparation for lifetime testing at Intel. So what we do is we initially take these threshold currents and laser characteristics before we have them aged, and then what we do is we package them up, carrier mount them, and wire bonding. So that's what this is. You'll see these chips. The lasers are on a chip, and they're mounted on a big carrier, and then wire bonded so that Intel can automatically test them. They age it at 35C and constant current injection. That they actually inject current at double the threshold, and then what they do is they test how long the laser lasts. And our goal is to basically increase this mean time to failure, or the amount of time that it takes for the laser threshold current to double, because we assume that's kind of the point where it no longer will serve its intended purpose. And so this is actually data from the past kind of few batches of lasers. None of these are ones I measured, but the ones I characterized, we actually just sent to Intel, and we're waiting on results. Hopefully we can get them next week. But if you look up here, this is a logarithmic scale for the mean time to failure measured in hours. And this mark here, 10,000 hours converted to years, is a little over 1 year. So if you think about putting it in a computer, you'd rather your computer processor not fail after a year. So we're looking to drive it up closer to here. This mark is the record currently held by University College of London, one of our main competitors, specifically on quantum dot research. We hope kind of expect that this newest batch will be up in this range with the measurements that come back at the end of this week. So on top of this, we would also like to continue temperature-based characterization for low temperatures, because if you look at a laser operating at low temperature, you can kind of reduce the chaos in the system and maybe see more ideal lasing. So if something is happening at room temperature that wouldn't happen at like cryogenic temperatures, then you can kind of notice the difference, and it can help you characterize how the laser is working. So future work on these lasers is hopefully to include low temperature characterization. And then I would like to thank Daewon Jung and another postdoc, Yating Wang, for guidance and graphics for this presentation, and then also Wendy and Jens for kind of continual advice, and then all the AIM interns for the weekly kind of critiques. So, thank you.